Okay, so this is like a brush up on integration, and so what we're doing is just like covering everything, all the main points that we cover about like just integrating overall. I'm not covering Simpson's rule and the trapezoidal rule, uh, because we'll just cover those later. This is just like simply about like the actual integral as a function and like not as a function, as an operation, and how we just use it. Yeah. Just a little brush up. Yeah, okay. So when we're working in 2-unit math, we identify that integration is basically the opposite of differentiation. And when we're using differentiation, we're trying to find the slope of a curve. When we do integration, we're trying to solve for the area underneath a certain curve. When we're dealing, okay, so then, so what happens is, when we do differentiation, it's basically like an operation, like adding, timesing, multiplying, squaring, dividing. So that's just an operation that we can do with certain numbers or with certain symbols, like polynomials. Yeah. So similarly, we can use indefinite and definite integration as well as differentiation as an operation. So something that we can do with numbers. And so what happens is when we're doing indefinite, it's purely just an operation. Definite takes advantage of this indefinite that we do, and then we use whatever results we get from our indefinite to solve for a certain area underneath a curve. And so we have also like a few shortcut tips, rules kind of thing to help out and to make things easier if you just pick them up like in exams, and they'll just help you out. And when we move on to extension 1 math or 3-unit, we go like a little bit further and we start learning a new integration technique, which is U substitution. So like when we're dealing with integration overall, like doing the definite integral is like not too hard, but like knowing how to do the indefinite integral is like one of the most important, like the base things, like in differentiation, right? If you don't know how your rules work, or like if you do your rules wrong, then obviously you're going to get the wrong slope for a certain point. So like you have to get the basics like fully like mastered, and then like all the harder stuff just gets really really easy. So anyway, let's just get to a few examples, right? Actually, like I'll do a generalization kind of. Okay, so when we do integration of like a polynomial, right? Just like x to a certain power. Why is it not working? Okay, yeah. Okay, so say if I had like if I differentiate x to the n, then I get me nx to the n minus 1, right? So I bring the power down, and then I subtract 1, right? So now we said that integration is the opposite of differentiation. So then if I have x to the n, and now I'm integrating in respect to x, right? So this is d over dx, differentiating, and that gets me there. So when I'm integrating, now instead of, so first we brought it down, like, yeah, multiplied by our power, and then subtracted 1. So this time around we have, so you see how we brought the power down first, and then subtracted 1. So first what we do, we add 1, and then divide by that certain number. So then I get x to the n plus 1 all over n plus 1. So it, along with it being in the opposite order of like things doing, you do the opposite thing overall. Kind of makes sense? I mean, and then because it's an indefinite integral, you have to add a constant. The reason why we do this is because now when I differentiate like this, right? Say if I differentiate x plus x squared plus 1, then that just gave me 2x. If I do x squared plus 5, I get me 2x again. So if I integrate 2x to get back to there, I don't know which constant I'm dealing with. I can be dealing with 1, 5, pi, some other number. We don't know. So that's why we leave it as just some constant. We know that it's not multiplied with x or anything, but we know that it's a constant. But we don't know which one. That's what we do in indefinite integration. Yeah? As a revision here? Okay. also, oh yeah, okay, so then another example, say if I do ax plus b, and if I differentiate this gets me, let's see, ax plus b all to the n power, yeah? So then I bring the n down, I bring n groups of ax plus b, and then I multiply by n, yeah? So, oh yeah, to the power of n minus 1, yeah. This is just the chain rule that we applied. When we're integrating ax plus b, x plus b, all to the n, remember how we said that was the opposite? So what we do is, now here, so then what we do, we add the power 1, so then it's ax plus b, n plus 1, right? And how we said, alright, this is not times a, this is not times n, this is times a, whoops, because now we're doing the chain rule, right? So then the inside, the differentiation of the inside will just give you a. Anyway, so then again here, how we added the power and then we divide, n plus 1. But the thing is, now here we times by a, we divide by a this time round. A groups of n. So then a is on our denominator. This is just an identity. These are just two identities that you see in the textbook. Yeah, this is I want to get started off because this like the beginning. Yeah. Anyway, so what I was getting at, an example. So then this just gets me the integral of x squared. So then I add 1 to the power. So then get x cubed, and then I divide by that. So then 3 is our denominator, and this is how we get it. Remember, we have to add the c. Always remember the plus c. There's so many marks lost. So many times where students lost marks and cried because they forgot this damned plus c. Anyway, okay, so the integral of 4 dx, okay, notice that there's no x's. So what I'm going to write is, I'm going to write this as 4 times x to the 0. X to the 0 is 1. 4 times 1 is just 1 dx. And this just gets me, let's see. This gets me, let's see, when I bring, now I add the power. So then I get, let's see, 4x all over 1, which is just 4x. Yeah. So the integral of 4 just gives me 4x plus c. Remember the plus c? Yeah. Anyway, yeah. So whenever you're removing the indefinite integral, yeah, you always have to have the plus c. Yeah, just keep that in mind. Okay. The integral of 4x to the 5th. Okay, as we said before, we subtract the power and divide. So then, not subtract. Whoops. We add the power of 1. So then 5 plus 1 is 6. So x to the 6 times 4, obviously, 4x to the 6, all over 6. 4 over 6 is equal to 2/3. So I'll write this as, I don't know, 2/3 x to the 6. I'll just write it this way because I can. Another important thing is when we're doing integration, right? Just like differentiation, we can also apply this. Say if I have like, okay, if I'm differentiating d over dx of 5x squared, right? What I can do is, because this is a coefficient of x, this coefficient of x can actually go behind, and then we can differentiate only the x squared. So it just gets 5 times d over dx of x squared. Now when I'm differentiating this, that just gets me 2x. So 5 times 2x, which again is just 10x. And you can just solve this yourself, right? In a very similar fashion, we can also apply this as 4 times the integral of x to the 5th dx. And so this just gets me, again, 4 times x to the 6th over 6, which just gets me the same answer. Okay, next up we have, let's see, 3x cubed minus 4x to the 4th plus 7x squared dx. Okay, oh, this looks a bit messy. But there are some similarities in differentiation and integration, and this is one of them. What I can do is, if I have like x to the 5th plus, I don't know, 2x to the 4th plus x cubed, right? And I'm differentiating the whole thing, of this whole thing, right? I can differentiate each term individually, right? So then that just gives me 5x to the fourth plus 8x cubed plus 3x squared, right? Squared, yeah. So in the same manner, we can split this integral into integrating each term by itself. Okay. A very important habit that you should get into the habit of. That sounds really redundant. Anyway, a good thing to get into the habit of is simplifying your integrals. So getting out any constants. You know how we did above here, right? How we got out the constant. A very important trick is to take out these constants because it makes the whole integral look simpler, and it is simpler to solve when you take out as many constants as you can and you want to break it down. That's how integration works. There is no I mean, there is a power rule, but there's no chain rule, there's no product rule, there's no quotient rule. Like, it doesn't get very straightforward that way. One of the best ways that you can integrate is just to break it down into smaller and smaller chunks that you can actually eat up, or you can digest, in a sense. Okay, so this just gets me okay, I'm going to split this up. Integral of 3x cubed dx minus the integral of 4x4 dx plus the integral of 7x squared dx, right? I can bring the minus in or out, but this is like a -1 coefficient, yeah? So I can bring that out as well. Okay, now I'm just going to bring all my constants out. This is just out of good habit, yeah? So I'm just doing this 3 integral of x cubed dx, and then this is minus 4 times the integral of x4 dx plus 7 times the integral of x squared dx. Okay, and then I'm just going to apply the same power rule that we played with earlier. So then I add the power and then divide by that. So 3 times, now x to the 4th power, all divided by 4. Minus, so, actually I'll explain this later, stop it. Okay, then I'll have 4 times x to the 5th, all over 5, plus 7 times, what's this, x to the 3rd, all over 3. Okay, yeah. Okay, and then out of all of this, I'm going to add plus c. The reason why I want to do that plus c at the end instead of having plus c, plus c, plus c, because if I add a constant plus some other constant, plus some other constant, I'll just get one other constant. If I add a plus c and b plus c, I'll get d, and I'll just get some other number, right? I'll just get another whole number. I don't have a coefficient of x or x to the something. Yeah, I just get some other number. And this number is just not of my concern. It's just I get some constant. Okay, just solving this, I just get 3/4 of x to the 4th minus 4/5 x to the 5 plus 7/3 x to the 3rd. Okay, moving on, we have 1 over x squared dx. Okay, so this is, I'm going to rearrange this and make this into index form, because this way it's easy to solve. X to the -2 dx, and then we applied the same way that we did our power rule before. So then we add the power. Remember that this is not -3, this is actually -1. Remember adding 1, so then we get x to the -1 all over -1. Now the minus just comes in front, that just gets me minus, okay, x to the -1 is just 1 over x, right? So that just gets me -1 over x. Okay, this is actually the integral of the cube root of x squared dx. Again, let's just write this as our index notation. So that just gives me x to the 2/3 dx. This just gets me, let's see, now I add 1 to this, so then I get x to the 5/3, all divided by 5/3. This looks really yuck. Okay, then I'm just going to write it this way, like x to the 5/3 divided by 5/3. Okay, that just changes it to, I flip the fraction around and multiply, right? So I get 3 times x to the 5/3 all over 5. Yeah, that's a 5 over there, just making sure. Alright, 10x squared dx. Okay, now as I was saying, out of habit, bring the 10 out. Integral of x squared dx. Oh wait, alright, I have to do the plus c. I keep forgetting. Everyone literally forgets this. You do not want to be caught forgetting this, yeah? Oh my god, how many times have I forgot this? Okay, yeah, remember, always remember the damn plus c. Okay, and then we have 10 times, let's see, now we add the power, add 1, so x cubed, all over 3. Now that just gets me 10 thirds x cubed. The reason why I like to write this, so this is my clear coefficient, and this is my x to the whatever power. It's really easy and noticeable to tell what is what. Okay, now I'm doing definite integration, right? So definite integration takes advantage of our indefinite integration, and we can use this to find the area underneath the curve. So then if I have x to the third power, right? That's just x cubed, yeah. So that just gets me, okay, I'm just going to I'm going to actually sketch this function more or less. Looks something like that, and it looks something like that. Yeah? Okay, so between -1, so I'm guessing this is -1, and this is like 2, yeah? 2 somewhere here, yeah? So then I'm sketching this area. I'm trying to solve how much area is underneath this curve, and this is between 2 and -1, right? And the way that we do this is using a pretty neat idea, right? So what we do is we first do the indefinite integral. So that's just the integral of x cubed dx. And so we get our answer, right? Answer. Right? And so with this answer, then we plug 2 into as x. We plug 2 as x. And then we subtract it from when we plug -1 in. Let me show you how, yeah? Okay, so how we do that is, okay, now we first do the indefinite integral. So then we get what? X to the 4th power, all over 4. Okay, now from this, okay, I'm going to write it. Now, like the normal, I don't know, the way that I would write it is then I would get square brackets. And then I'll write this in, x to the 4th, all over 4. Finish up the square brackets. And then you write -1 on the bottom. And you write 2. Okay, I'm just going to write here, okay, equals. Okay, then I sub 2 in, so then I get 2 to the 4th all over 4, and then I subtract it from, so I sub 2 in first, and then I subtract it from when I sub it in, sub 1 in, -1, sorry, -1, all to the 4th, all over 4. So you sub the top one, and then sub the bottom one, like, and you subtract them 2. So that just gets me, let's see, 2 to the 4th is what? 2, 4, 8, 16. 16 over 4 is 4. And that's just subtracted from, now, -1 to the 4th power gets me 1. So that's just 1 over 4, which is 1/4, which is equal to 3 and 3/4. That's my answer. Yeah? And now here there's no plus c, because this is like a certain area. Like, you know, when we're dealing with indefinite integrals, then we'll have our plus c. Okay, now a 1 and -1 of x cubed minus x dx. Okay, so when we, this is like a special case kind of thing. What we should notice is that first that we have a -1 here and we have a +1. Upside down, underline, I don't know. Okay, so we have a 1 and a -1. You see how that they're opposites of one another? And that we have a purely odd function. Odd function. Okay, you can tell that's an odd function because x cubed is an odd function and x is an odd function. Also, you can see that they both have odd coefficients and there's no even function in here. So then this function is purely odd. I could get a graph of this, but like, you can graph this, right? I'm gonna pretend it's gonna look like this. I don't know, I'm guessing it looked like this. It's still a cubic, so it looked like this. So you see it's kind of symmetrical here. And now if I take it from 1 and -1, so then imagine if this is 1 and this is -1, right? What happens is if we take an area below the x-axis, it's counted as a negative area. It's really odd to think about it that way, but because it's below the x-axis, we count it as negative. And because the amount of area here is the same as the amount of area here, then we get a total area of 0. Because this is a negative area A, so I'm going to call this area A, and this would be negative A, right? A minus A would be 0. And so we automatically know, without even solving, that we get 0. And I can prove this to you, like, simply. The integral of x cubed minus x dx just gets me, I don't know, that's just me x to the 4th over 4 minus x squared over 2. And then I sub 1 and minus 1. So then I sub 1, that just gets me 1/4 minus 1/2, all subtracted from, now let's sub minus 1. So minus 1 to the 4th power just gets me 1/4 again, minus 1/2 again. And you see how they're both the same thing. So again, we just get 0. We always get 0 if we have a purely odd function, and we have 1 and minus 1, or we have our two bounds, that's what we call them, bounds, if our two bounds are negatives of one another. This is like a special case. Another special case is when our upper bound and lower bound, that's what we call them, upper above 1 and lower bound below, when they're both the same thing, basically the area that we're trying to find out has no width. If something has no width, we can't really solve for the area, we just write it as 0. Because, you know, if we write it this way, right, area is equal to length times width, right? And if my width is 0, obviously my area is going to be 0. So we already know that this is all equal to 0 as well. Okay, so again, as I was saying, this is an odd function, and we have 1 and minus 1. So we automatically know that this is equal to 0. Again, you can actually do the long way and you can solve it, but like, this is just the special case that you should identify. Okay, now this is a different case. Now we have a different power. We have an even function now, and now these bounds are negatives of one another. Now let's just visualize this, right? Understand what's going on here, yeah? So then we have a parabola looking thing. My 10 out of 10 parabola drawing skills, yeah. And then I have my 1, and I got my minus 1, right? And I have this area, and I have this area. And that's the total area that I'm trying to solve for, yeah? And so this is, oh wait, not minus 1 and 1, this is minus 2 and 2. Sorry, I didn't see that over there, yeah? So minus 2 and 2, and this is my two areas, right? Notice that the areas are of the same magnitude, they're the same size of area, right? And so basically I can tell that this is equal to twice the area from 0 to 2. See how that kind of makes sense? Because I can flip this. I can flip this over to the other side, right? And then it would be like double the area because it would be perfectly symmetrical, yeah? It's to do with the symmetry here, yeah? So then I can write this as 2 times the integral of between 0 and 2 of x squared dx. This just makes it really makes it easier to solve, because now when I sub 0 into this, then you'll see. Okay, so the integral of this, then we just do the indefinite integral. So then I'll just screw the equals, yeah. So then I get the integral of x squared dx. That just gets me, what do I get? I get x cubed all over 3. Okay, so this whole thing is equal to 2 times that square bracket thingy that we were saying before, x cubed all over 3. And I do it between 0 and 2. Now I sub 0 in. Now when I sub 0 in, this whole thing becomes 0. That's what makes 0 really special here. When I sub 2 in, then I just get my answer. 2, and I sub 2 in, and then I subtract it from when I sub 0 in. So then this makes it very easy to solve. 2 times, let's see, 2 cubed all over 3 minus 0 cubed over 3. This just gets me 0, so that goes away. Bye-bye. And so then I get this. Now I can write this as 2 to the 4th over 3 if I want to. But I'll just get the exact, the nice clean number, or whatever number that we solved before. That's 16 over 3. Yeah. That's equal to the thing above, not that. Yeah? Okay. Alright. So now we're on to 3 unit. So then we start using a new integration technique, which we call U substitution. So then if we have, okay, so now I have a pretty messy looking integral thing over here, yeah? And we are often told, especially in 3 unit, you're almost always told what U is equal to, and you have to use this U, and we have to sub it in, and we have to solve with it. Okay, so how U substitution works is, what happens is we let U equals to 1 plus x squared, right? And then what we do is we write it as d, now we differentiate this basically, du over dx just gets me, now I differentiate this, I get 2x. Yeah, this 2x and 2x here is not a coincidence. This is actually made, the question is manufactured this way. Okay, so then what I can write it as is, let's just put it this way, like a kind of currency exchange, right? Then I can write it as du is equal to 2x times dx. I know you can't really do this with, or like differentiation, when we're doing like du over dx, we can't treat it like a fraction always, but sometimes you can. Like that's what our math teacher told us, right? Dy dx or du dx is like a fraction, but it's kind of like not. It's really, really ambiguous in that way, but we can do this in this case, okay? So if I want to get me a du, right, I have to have a 2x somewhere, and I need a dx somewhere, and they need to be multiplied. I have a 2x multiplied by dx over here, so I can replace those two with a du. So that just gets me the integral of 1 over 1 plus x squared du. Yeah? Now, I can't integrate, now I have an x here and I have a u here. But what we can do is, now we said that u is equal to 1 plus x squared, so then I can substitute this in, and that's why it's called u substitution. The integral of 1 over u squared du. Okay, now this looks really, really simple. And this is one of the main, this is one of the key ideas of integration. You have to break things down or make things really, really simple for yourself from something that's really complicated into something really simple so you can actually integrate it. So this is just the integral of u to the minus 2 du. U, that's u, yeah. Okay, this gets me, now I add the power, so then it's u to the minus 1 all over minus 1. That gets me minus u to the minus 1. Plus c, yes, I didn't forget this time. Okay, you might think that you'd be done, but there's an important step. Our question is in terms of x and not u. So we have to write our answer in terms of x and not u either. So then we have to write it as minus, now we have to write it back in 1 plus x squared to the minus 1 plus c. If you really want to, you can write it as a fraction just to match it up. But yeah, 1 over x squared plus 1, same thing, plus c. Yeah. Okay, another one. X squared root of x cubed minus 1 dx. Ew. This looks really yucky, yeah? Pretty messy, pretty cloggy. Okay, so as we did before, we differentiate this. Differentiate. Du over dx is equal to 3x squared. That's it. Yeah? Okay, so then if I want to convert between du and dx, is equal to 3x squared dx. Okay, we can do that, right? We have a dx. We don't have a 3x squared. We have just x squared. Then what do we do? What we can do is basically we're pulling the 3 out of thin air. But the thing is, we have to maintain that kind of balance thing going on, right? What we can do is we can write the integral of 3 over 3 times whatever we have here. So that's x squared root of x cubed minus 1 dx. Yeah? Now this 3 and this x squared can, so these two can go with the dx, and they all can be a du. And I have a 1/3 left over. The integral of 1/3. Okay, and this becomes, okay, this is u, so the square root of u du. Yeah? Now this 1/3 I can bring it back out. Then I have 1/3 times the integral of square root of u du. Now this gets me, let's see, this is u to the 1/2, right? 1/3 times the integral of u to the 1/2 du. Now we apply the same power rule as before, right? Then we get, let's see, 1/3, yeah, times, let's see, u to the 3/2. 3/2. Okay, I'll just clean that up. U to the 3/2 all over, alright, this is 1.5. 3 over 2 is just 1.5, yeah? Okay, so 3 times 1.5 just gets me 4.5, so I'll just write it as that. U to the 3/2 all over 4.5. I can multiply both sides by 2 to get whole numbers, it really doesn't matter. 3/2 x. So then I get 9, yeah? Okay, now we have a little bit of trig functions and stuff, but essentially the same operations happen. We should recall that when we differentiate sine x, we get cos x. Differentiate cos x, we get back to sine x. Here, the smart choice is to use u equals sine x, because if we use u equals cos x, right? I'll show you the issue here, yeah? U equals cos x, then du dx is equal to minus sine x. Sorry, this is not sine, it's minus sine x, right? And then du equals minus sine x dx. Okay, so we have a sine cubed x, so we can easily do that, right? Then we have the integral of, let's see, sine squared x, right? And we have a minus, right? So minus sine squared x times minus sine x gets me plus sine cubed x, right? Sine squared x, u, and then I have me a du. Right, now I have an x, I have a u, and I have a du. I can only integrate when everything is in terms of u. Then I have to like spend an extra few steps to actually change this in terms of u, which gets pretty messy and gets, you know, gets really annoying and stuff, right? So that's why we would use sine x, because this is sine cubed x, which makes things rather easy. So that just gets me du dx is equal to cos x, right? Du equals cos x dx. So this is like a currency exchange, as I was saying. If I want to convert between du and dx, I need a cos x somewhere. So I have made a cos x and I have a dx, so I can easily change that into a du. Remember how we said this is sine cubed x, right? And we said u equals sine x, right? So then this is u cubed. So this is the integral of u cubed times du. Not times, u cubed du, let's just call it that way. Then we get, let's see, the same power rule that we said before, u to the 4th over 4. Remember, we have to write our answer in terms of x. All right, plus c. Yeah, so then we have sine x, sine to the 4th x, sine 4x, all over 4, plus c. Any other examples? No. And we are done. Sorry it took some time, but yeah, I hope you enjoyed, and I hope you get it, yeah? That's what's important.